Okay, so here are some notes from our homework 3. So I'm first going to talk about uh, exercise 5. Yeah, so we are given log of y have a linear form plus epsilon, and then epsilon following a normal with a mean 0 and the standard deviation sigma. Yeah, so we are interested in the expectation of y as well as the variance of y. Yeah, so so first of all, we need to comment on the distribution for this new random variable that we define as log y. And yeah, all these are non-random. And the only random variable is the epsilon. So we are basically just shifting the random variable epsilon by this amount. So we are just shifting away from 0 by this. So the new mean is just beta 0 plus beta 1 x, and if you want plus 0. We do not have a scaling factor on this new random random variable here. So the variance or the standard deviation of the new random variable log y has the same variance as the epsilon. And if there's a epsilon, then you also need to you need to also scale the variance of the new random variable. Okay, next we need to use the moment function to solve this problem. So let's write down capital M for log of y and a function of t. And we know log of y now is following a normal distribution, so we can use the homogeneous function for log of y, which is t multiplied by mean. And the mean of this log of y is just beta 0 plus beta 1 multiplied by x. Then plus 1/2 t squared, and the variance of the new random variable. And the variance of this new random variable is just sigma squared. Okay, so we have that. There's one more equation that we can set up here. This is just a definition for e of t x. And then this random variable x here is just the log of y. Okay. We can further elaborate that by changing the power of the y, by bringing the t as a power of y. And then the exponential operation and the log transformation also cancel out. So we have the simple form here. And by looking at that, we notice that when we set t equal to 1 and t equal to 2, we are able to get the first moment of y and the first moment of the variable, the second moment of y. And that should help us to evaluate the expectation of y and the variance of y. Okay, yeah, so now we just need to evaluate. T equal to 1 is equivalent to expectation of 1. Yeah, so e beta 0 beta 1x plus 1/2 sigma squared. When set t equal to 1, t equal to 2, you will have the second moment, and that would be 2 times beta 0 beta 1x 1/2 2 yeah. So and then with these you can have variance of y equal to expectation of y squared minus expectation of y. Yes, the second moment minus the square of the second moment. And then you can evaluate the variance of y as well. Yeah. Okay, so next let's take a look at part B. We are given y1 bar, and this is denote a group of n samples draw from say the first sample, and then each of the yi or actually the underlying population has the distribution of epsilon and sigma. So we are interested in the probability of y 1 minus the average of a second sample, and then their absolute value less than sigma over 5. This particular event has a probability of 0.99. So this is the probability, and we are asked to find the number of n. Okay. Okay. Yeah, so first of all, let's comment on the maybe on the average of y. And regardless of either this is the sample from y1 or y2. Okay, so the average is usually defined as 1 over n summation of yi, each of the yi coming from a normal. So let's find out the average, the expectation of this. So we will have n copies and then summation 1 to n expectation of yi. Each of the yi is following having a mean of mu. So this is just 1 over n copy of mu, and then that's equal to mu. For the variance of 1 over n summation of yi, this is equivalent to 1 over n squared when you bring out the constant term. And then the summation can also be moved outside the variance. This is because they are IID and the variance of yi. Again, each of them follow a normal distribution with variance sigma or sigma square. So we'll have 1 over n squared, n copies of sigma square. So we have sigma square over n. Okay. So this is the distribution for y bar, also following a normal mean mu sigma over square root of n. This is the standard deviation. Let's comment on y1 bar minus y2 bar. So the expectation of that if you want, you can also elaborate on that, but in the end, you will just see that this is just the mean from y1 and the mean from y2 that will give you a 0. Yeah, but this is not the case for the variance of y1 minus y2 bar. So we can elaborate on that in the following way. Summation yi. So maybe I will use subscript here, a superscript here to denote this is from the first sample. And this is from the second group. And the I is just referring to how many samples that we draw in that group. Yeah, so they all share a constant term. So let's bring that. Maybe let me just jump a few steps, and then the variance of yi from group 1 minus yi from group 2. Okay, so while a particular observation, they can be different numbers. So just intuitively, they're not just going to become 0. So here we want to comment on the variance of a difference. So actually, the variance of difference, let me group. Okay. Let me group that. So we need to calculate the variance of yi, which is sigma square over n, coming from here. And yeah, and here this is actually -1 multiplied by that. So so don't forget, when you bring a constant term outside the variance, this is actually square. So square of -1. So you will have another copy from the second sample, from the second group. And don't forget, you need to multiply by 2 times covariance. Yeah, but it just turns out that they are independent, so they are all 0. So there's no correlation or no covariance between the first group and the second group. So that's why you have a 0. But usually you have the variance of y1, variance of y from the second group, and then plus the 2 times covariance. But in this case, they are all zeros. Yeah, and then that should simplify to 1 over n squared, n copy of 2 sigma over n, ends up to 1 over n 2 sigma squared. Okay, so now we can maybe comment on here that y1 bar from the second one minus from the second one, having a normal distribution with mean 0 and 2 sigma square over, let me double check. This is a square, n square, and then altogether square root. This is the standard deviation here. Yeah. Okay, so now back to the events. So we have y1 bar minus y2 bar. We need this. Yeah. So we are going to perform the transformation to here, the things that inside the parentheses. So we want this less than sigma over 5. So let's perform the same transformation by standardizing. Minus 0 over 2 sigma square over n square. Same transformation on the right hand side. And we want this event actually because we have the absolute value, so this is actually or equivalent to a two-sided problem. So we want the middle part to have a probability of 0.99. So you just need to find out the quantile for a normal. After you standardize it, this thing follow a standard normal distribution by standardization. And then you just need to find the quantile for 0.005 because we also have a 0.005 on this side. And to find the quantile here, and then setting the right hand side. You can either use one side, the left hand side or the right hand side. So here we're just going to use the right hand side, but you need to find the quantile of that. And that it turns out, if you look up a table, it will be that. So 2 sigma square over n square, that, and then you set it equal to the quantile. And yeah, the sigma square will be cancelled out, and then the only unknown is n squared. So you should be able to find out what is the value for n. So basically, the sample size that you need to achieve this kind of to make sure this event has a probability of 0.99. Yeah. So the key idea is that you need to recognize the distribution for this, which turns out to be a normal, and then go back to here to set this one equal to the quantile of 0. This is the quantile of 0.9 95. Yes. So when you look up the table, you should look up that, and this is the quantile for negative 0.005. But the area, the sum of them should be 0.01 to make sure that area under the curve is probability is 1. Yeah. So set up the quantile by letting this equal to the quantile, and that should give you the number of sample that you need to achieve that. Okay, so that should conclude exercise 5. Let's also take a look at exercise 7. Okay, so we have yeah, so we have x following a normal mean mu sigma. Yeah, so the homework, it says in homework 1 we use the CDF method to find y(ax) plus b. Okay, so we're scaling this random variable by a factor of a and then shifting by amount of b. And the y following a new normal ax plus I think it's a, yeah. So a mu plus b, and then this should be a sigma. So now we just need to use the moment function method to find that, and this is equivalent to the moment function of ax plus b function of t, and then e raised to the power of ax plus b. Let's also going to simplify this by bringing the constant term. So this is coming from the the exponential of t multiplied by beta, which is irrelevant to a random variable, so we bring it outside the expectation. At multiplied by x. So by doing this kind of rearrangement, we get e of t multiplied by constant b, and we have the moment function with respect to the original random variable x, but this time the t become at, the new t here. Yeah. And now let's visit the moment function for a general normal distribution. So we still have the constant part, and then e multiplied by the function of this is the new t multiplied by the mean, and the mean is just mu plus 1/2, and then the new t square. So you need at square, and the variance just the sigma square. And we need to simplify it to recognize the form of generating of the moment function. So e t multiplied by b plus product of exponential is the exponential of sum. So we also have a mu multiplied by t plus 1/2 a square t square sigma square. And let's just group it, make it more. So yeah, here you have a multiplied by mu plus b altogether multiplied by t, and you also have 1/2 t square and a sigma square. Okay, so now you can consider this as your new mean, mu star, and this as your new sigma star, a new variance. And now you can claim that y following a normal with this mu star equal to a mu plus b. The mu is referring to the original mean of a random variable x, and the variance sigma square is just a square sigma square. And you probably want to take the square root to refer to the standard deviation. Yeah. So because of the uniqueness theorems, you can just read off from this form to recognize this is also sharing the same form as a moment function of a normal distribution. So you have this new mean and the variance. Okay, let's see. Okay, so that should conclude part A. Let's see part B. We have a random variable following gamma beta, a gamma distribution. Let y equal to exponential of u. We are interested in, okay, first find the PDF of y, and then expectation of y, and then the variance of y. Okay, so that will be the problem here. In doing so, we need to find out, or we need to use the CDF method first, to starting with the CDF of y, equivalent of y less than a particular observation, replace it by our definition of y back to random variable u. Equivalent to the random variable u less than log of y. Okay, and now we are going to take the derivative. Maybe I can just write one more equation here. So here we transfer back to the CDF of u from originally CDF of y to CDF of u, but we need to evaluate at this particular number. Okay, so to get the PDF, we need take the derivative of the CDF of this u and evaluate at this quantity here. So first of all, let's use just to make sure that we don't forget the chain rule. So we take the log derivative with respect to the quantity inside the parentheses. So we have 1 over y, and then we have the PDF of the u, and that is the. So here I'm first going to write the u of alpha minus 1 because u following gamma distribution, and then exponential of u over beta over gamma function of alpha and the beta raised to the power of alpha. But we need to represent this as a function of all y. So we need to rewrite u equal to log of y. And changing all the u here. So 1 over y multiplied by log of y raised to the power of alpha minus 1. Log of y over beta over a gamma function alpha beta alpha. So this is the PDF of random variable y. We use a lowercase here. So this should first answer the question of PDF of the random variable y. Next, we are going to find the expectation of y. So first, maybe let's, because maybe it's difficult to tell what distribution the random variable y follow based on this form. So we are going to use the momentary function of the random variable u that we already know is following gamma. So we're going to start from there to answer the question. The momentary function of a gamma distribution is just 1 minus beta t raised to the power of negative alpha. This is just the known form for the momentary function of a random variable u that follow a gamma distribution. Yeah, and let's also set up another equation, e of, let's see, exponential of t multiplied by log of by u. But here we need to make the change for u, which is the log of y. So we bring the log of y inside. Yeah, and as in the earlier previous example, we can rewrite this as expectation of yt. as in the earlier example. And yeah, so our goal is to find the expectation and the second moment of y. So we can also set t equal to 1 and t equal to 2, and then evaluating this equation here to find the expectation of y. So this is just 1 beta minus alpha, and the second moment is just set t equal to 2, 1 minus 2 beta negative alpha. And then from here, you should be able to find the variance of y. Okay, yeah, so from the known distribution, using the CDF method to find the PDF of a new random variable y. And also, the second part is that we use the moment function of the known random variable and bridge between. Well, this is just a special case, so that's why we can do it in this way. And then we make the connection and then evaluate t equal to 1 and 2 to find the moment of the new random variable y and the variance of y. Okay, next, let's take a look at question, maybe exercise 8. So let's see. X is a n by 1 random variable with a vector of and the matrix sigma. So this is yeah, we actually do not need to know the distribution. Yeah, so this is just referring to a general mean vector and the variance matrix, but it does not necessarily mean it's following it normal. It just can be just referring to the general mean and the variance. Suppose y equal to x minus b. B is a non-random vector of constant. Okay, so this is also n by 1. Show that the expectation of x minus b transpose a multiplied by x minus b is equal to a trace of in that form, but maybe I'll just derive all the way to the end to see if equal to the right hand side. So here, first of all, recognize that this is 1 by n after the transpose. This is okay. Also, n is a is a n by n, and also this is n by 1. So we have a scalar here. That means we are able to use the trick for trace. So x minus b transpose a x minus b. Then we can apply the cyclic rule here. So let's expectation of trace of a x minus b transpose. Okay, then we have a trace of expectation. Maybe I can also jump a few steps to make a is a constant here. So when we evaluate the expectation, we can move it outside. And we have x minus b transpose. Closing that. Okay, yeah, so let's see. I think one thing we can comment about this is there are a few ways, but yeah, so maybe let me elaborate on the expectation first. We have XX transpose. So here I'm just going to expand this. Minus 2x maybe not doing this way. So yeah, maybe we can view it as this. So if you still recall from earlier where we have the y transpose is equal to the mean of variance multiply plus the mu transpose. But here this is referring to the variance of y and the expectation of y. So here we just need to see that, so when x following a distribution, and then you're also shifting by a constant of a b, so you are equivalently shifting the mean by b, by this constant b, but the variance stay the same. So yeah, by recognizing that, we can say that so here we just like let y equal to x minus b. Then this equation, the right hand side still holds, except that now the variance is referring, the sigma matrix is referring to variance of x minus b, and then plus the mu transpose. But the mu here is the mu minus b, so you have mu minus b, mu minus b transpose. So yeah, this is just a side note that we can comment on that. So let's revisit that as trace of a. So now we are going to substitute this part. So plus mu minus b, mu minus b transpose, closing that, and yeah, so let's see if we can further elaborate that. Yeah, let's distribute the terms here. So we have a trace of this A multiplied by the sigma matrix. A multiplied by sigma, and also trace is a linear operation. So we have a trace of A multiplied by mu minus B, mu minus B transpose. Okay, so this, let's make it stay the same, and we are going to change the order using the cyclic rule. So write it in terms of this, closing the trace. And let's see, yeah, so I think this is equivalent to the problem statement we want to show. So this is a n by 1. After transpose, it will be 1 by n. We have a n by n. This is a n by 1. So in the end, we will have trace of A sigma plus trace of a constant. So it's just a constant. So mu minus b matrix of A, mu minus b transpose. Okay, so yeah, this is just equal to the right hand side that the question asked. That to show that the original, the left hand side equal to the right hand side. Yep. Okay. So next, maybe let's see. Maybe take a look at question 9, and this will be our last problem. We have a multinomial. Okay, multinomial. And which have a homogeneous function. So this is a vector of t because we have let's see, r of them. So it's a r by 1 vector. And having the form of p1 et1 plus all the way to pr etr. Okay, so that's the homogeneous function. Also raised to the power of n. Okay, so that's the homogeneous function for a random variable x that follow multinomial distribution. We are asked to find the PDF of x1. Okay, so yeah, we can directly setting the t's that we are not, the t's that associated with the random variable that we are not interested. So this is the homogeneous function of the first random variable, but setting all the rest of the t equal to 0, the one that we are not in, the t that associated with the random variable that we are not interested. So we just have et1 remaining, but p2 e to the 0 plus p3 e to the 0 raised to the power of n. And here we just have a summation of p2 plus p3 plus all the way to pr. And then given the constraint that from 1 to r, pi equal to 1, so that the summation from p2 to pr is just equal to 1 minus p1, the first element. So in the end, we will have t1 et1 plus 1 minus p1, altogether raised to the power of n. And then from here, we can recognize that this is the homogeneous function for a binomial distribution. Yeah, so we can claim that the first random variable that coming from a multinomial distribution, having a binomial distribution with a number of trials n and the probability of p1. Okay, and then yeah, the second question is referring using the theorem to find the mean and the expectation of mean and the variance of x1. So yeah, I think you can use you can take the first order derivative of the homogeneous function and set it equal to 0 to find the mean of x. And now we just need to comment on using the theorem to find the variance of x1. So here we just need to take the log of the moment-generating function for this multinomial random variable. And this is equivalent to n multiplied by the log of that. So let me just copy down here, plus PR multiplied by E multiplied raised to the power of TR. So in order to find the variance using this theorem, we just need to take the derivative twice with respect to the t1 that associated with the random variable that we are interested in. So yeah, let's denote this as phi of t, which is just the log transformation of the moment-generating function. So we are interested in the first random variable. So let's first take the first order derivative with respect to t1. So this should be a constant n in the front, and then the sum in the denominator, and multiply by the chain rule. So the things inside the log. So the things that involving t1 is only the first term involving t1. So we just call and then just multiply. So this is just applying the chain rule for the things inside the parenthesis. We have the constant multiply by itself. So this is just the first order derivative. We also need a second order derivative to get the variance. So here we just take another derivative from phi 1, also with respect to t1. So here we need to use the quotient rule for the derivative. So let me make a side note here. So this is just the f prime multiplied by g minus g prime multiplied by f over g squared. Okay, so let's first complete the denominator here. Okay, PR, ETR, altogether square. So that should be the denominator. Next, calculating the derivative of the numerator. That is just itself. Multiplied by g. Yeah, maybe let me just copy down the entire thing here. T1 plus PRETR. Okay, and then minus g prime. So again, this is only P1 ET1. So the derivative of the denominator, so only the first term involving t1, so it's still going to be that multiplied by f by the numerator. So n multiplied by p1 multiplied by et1. Okay, so let's group things together. We will have, maybe I'll just leave it in this form. And now we're going to evaluate the variance. So just set let t equal to 0. So we just need to plug in everything, let all the t's equal to 0. So we have np1 e raised to the 0, and then p1 e raised to the power of 0 plus pr e raised to the power of 0 minus p1 squared E0, one copy of n, E0. And then the same thing here. So I'm just going to maybe not write down everything, but we just have a sum to P1 all the way to PR. And then by constraint, this is equal to 1 in the denominator. So in the end, we will have NP1 from the denominator minus P1 squared multiplied by N divided by 1. And this is just P1 N 1 minus P1. And yeah, you probably also recognize this is just the variance of a binomial distribution from NP1. So from your part A, you should be able to get this is N multiplied by P1. And then from part B, by using this theorem, we are able to get this is NP1, NPQ, so N minus P1, 1 minus P1. Yeah, so that should conclude part B. And let me just briefly comment on part C. So when you want to, when applying the theorem, when we take the log of the homogeneous function, we're achieving this phi, and then we take the first order derivative with respect to 1. When you want to calculate the covariance, you just need to take the derivative, so the first order derivative with respect to the variable of interest. So here just denote that as phi I. So this is the Ti of the log of the homogeneous function. When you're calculating the covariance, you need to calculate the derivative with respect to another Tj from phi I. So the only difference is that when you taking the second order derivative, you just need to make sure this f prime, g prime are with respect to Tj, but not Ti anymore. So here, our second order derivative is also with respect to Ti. And when you're evaluating the covariance, you just need to make sure that this is with respect to Tj in your second order derivative. And you should be able to have a final answer of a Pi, Pj as your covariance of xi and xj. Okay, yeah, so same procedure, it's just the second order derivative, you need to take the derivative with respect to Tj, a different component to your first order derivative. And that should conclude your question, part C. And yeah.